The Doppler effect is a perceived change in frequency when you have a difference in motion between the observer and something that's emitting a sound. Okay? So, or it could be light. In our case, we're going to be talking about sound since we're dealing with sound waves. So let's say that you are here, and let's say that we have some other person over here that is making a lot of noise. Okay? Or maybe they're carrying a boombox, like I mentioned in class, if someone actually had a boombox nowadays. But let's pretend that they have something that actually ends up giving off a lot of sound. Okay, so they're the source. This person is going to be the observer. So as this sound travels out, it's going to travel out spherically symmetrically from how this source is emitting the sound. And what I'm drawing here are what we're calling the wave fronts, or basically they're a way to write the peaks of the waves. Okay, you could all classify them as the center of the waves or the troughs of the waves either, but basically they're going to be the places where the wave is highest or most compressed as it is coming towards you. So it's a way to measure, basically, the wavelength of your wave. So the wavelength would be this part right here, which would fall on your ear. Okay, so as the difference between the length distance between the two peaks right there was going to be the perceived wavelength, or the number of waves that hit your ear per given time is the perceived frequency or pitch. So let's say this person is standing still, and you are standing still, and this person is emitting a note at 440 hertz. Okay, say that they have some program that lets them just do that, or they're singing, say, and they're hitting an A at 440 hertz. Well, you would hear that at 440 hertz. But now what happens if this person is in motion? If they start walking towards you? Well, what happens is that that person, he or she, is actually still emitting that sound wave, still at 440 hertz, as they're walking. But what happens is that when the first pulse is emitted, okay, then that spreads out from here. But now the person has moved this way. And so this wave has actually spread out more. That's the original wave. And now we have over here the person has actually emitted the next one. So what happens, and this is an exaggerated picture, these two wave fronts are much closer together than they were before. And your brain, your ear, can't tell the difference of each individual wavefront. It feels the net result of all of that coming. And so what happens is that your ear will end up thinking that this wavelength is a lot shorter than it actually was if the person were at rest. So that means that the wavelength is shorter, the frequency is bigger, you'll hear a higher pitch than you would actually have heard if the person were standing still. Okay. So now, let's say that the person is moving the other way. Okay, there's our sound maker. Okay, so he sends out the first pulse, which then, of course, ends up spreading out with time as it moves on. But this person is now moving over here, sending out the next pulse. And so this wavefront and this wavefront that are coming towards your ear are much more separated, much further apart than the wavefronts were in the other case, or when they were just standing still, when that person was just standing still. Okay? So your ear now instead thinks that it's hearing a longer wavelength, or a smaller frequency. And so you actually would observe a lower pitch. You would think that it was a lower note than the 440 hertz was before. Okay? All because of the relative motion between you and the source. Now, the source is not moving, you could be doing the same thing. As long as you're moving towards, it's going to sound like the frequency is higher, because you're going to be encountering each wavefront before you should have. Okay, if the thing were standing still. You yourself would actually be decreasing the distance between waves because you're moving towards the source. Or the other way around, if you're moving away, then you are, with every step in that velocity, well, and you're, not in that velocity, with every step in your motion, okay, you are increasing the wavelength because you're making it a longer time for the wave to fall on your ear. Okay. So if it depends on the relative motion between the observer and the source. If they're moving towards each other, then you're going to have the situation where you had the frequency increasing. If they're moving away from each other overall, then you end up with a situation where you have the frequency decreasing. And so we can talk about what this means mathematically. We derived this in class, so I'm not going to go completely through all the derivation for that. But what we end up seeing is that the observed frequency is related to the frequency that the source was emitting by a certain multiplicative factor. Okay? And so this depends on two different cases, if the source is moving or if the observer is moving. So if the person with the boombox is walking back and forth, or if you yourself are walking back and forth or running back and forth, okay, those are, they end up having the same sort of Doppler effect, that the frequency will increase if the relative motion is toward each other, or the frequency will decrease if the relative motion is away from each other. But we have to represent them differently mathematically. And so what ends up happening is that you have the frequency that's observed is the frequency that's been emitted by the source, where a small s down here stands for source, this is for observed, is equal to, they're related by the speed of sound, which is this v right here, speed of sound plus the speed of the observer divided by the speed of sound, assuming that the observer is moving and not that the source is moving. Okay, so if Vs, or V source, equals 0, you get this. Okay, now let's look at this for a second. So we have V plus V observer divided by V. If this V observer is a positive number, then this whole thing right here is bigger than 1. And so the observed frequency is going to be bigger than the source frequency. So that positive value of V observed is going to correspond to the case where you have them relative moving toward each other. So the source is here, the observer is moving towards the source. Now, if that were the other situation where the observer is moving away, then this would need to be a lower number than 1, because the frequency is going to be lower. So you have a negative that goes into there for the V observed, the sign for the velocity of the observer, for the situation where it's going away. So the V observer, as a positive number that goes in there, is moving towards the source. The V observer, that's a negative number, moving away. From the source. Okay. But then you can look at the other situation where instead of the source not moving, we have the observer not moving. You have to end up with the same situation where if the relative motion towards each other is happening, you get a higher frequency. If the relative motion away from each other is happening, you end up with a lower frequency. And so the derivation that we did in class showed that the observed frequency is still equal to the source frequency times a multiplicative factor. That multiplicative factor in this case is the speed of sound divided by the speed of sound minus the speed of the source. Okay. And so let's look at this the same way we did this case up here. If the speed of sound is smaller, not smaller, if the speed of sound is a positive number in here, then that means that this is going to be less than the speed of sound in air. So this is the speed of the source right here. I think I may have just misspoken before. If the speed of the source, okay, is positive, then v minus that positive number is less than v. So we have v over something less than v, which means that we have a number bigger than 1. And so that situation means that we have an observed frequency that's bigger than the emitted frequency. And so that corresponds to the situation where the source is moving towards the observer. Okay. So if Vs equals positive, that's moving towards the observer. Okay. So now, in the other situation, if Vs is negative, this denominator here becomes bigger than V. So a V over something bigger than V, that's a number that's less than 1. And so that times the source frequency means that you're going to have an observed frequency that's less than the source frequency. So that means that you end up with the situation where you are perceiving a lower pitch that's corresponding to the source moving away from the observer. Okay. So this situation where you have the source not moving, and this situation where you have the observer not moving, but you can indeed put those together in a general equation, which says that the observed frequency is equal to the source frequency times V plus V observed divided by V minus V source. And then you use the same conventions that I mentioned here, that you put in a positive number for the V observed if it's moving towards the source, you put in a positive number for the V source if it's moving towards the observer, and vice versa for the negatives. Okay? So that would be how you would deal with that in case both are moving. If one of them is not moving, like say the source is not moving, you just get rid of it, and it looks like the original case that we just had. Okay? But it's all about the relative motion of the two things, the observer and the source. If there is a net relative motion between them, then you're going to end up with a change in the perceived frequency. If there's no movement, then what happens is that the frequency is the same as what it was emitted, as what's perceived. Okay. There's something else that can change how you perceive the sound, and that would be if there's constructive or destructive interference going on, like we mentioned with the transverse waves. You can have constructive and destructive interference along with this too with sound waves. So if we have two speakers that are emitting sound, these are supposed to be my sound emissions coming off of here, okay, they're going to be traveling in waves that are going to be spreading out over time. Okay, so this one will be doing the same thing. Okay, and there will be places where the sound waves will actually cross each other in certain configurations to give you nicely constructive interference. There will be other configurations where you end up with a situation where you have destructive interference. This place right here in the middle is a good place to look at for constructive interference. Okay, if we are again imagining these are the peaks of the waves, both peaks are present right there. Both peaks are present right here. Both peaks are present right there. So instead of seeing the effect of one of the waves, you're going to see the overall effect of both of the waves, seeing double the peak. Okay. And so it depends on where you are in relationship to these to be able to hear this. Because you would only hear this if you're at that spot. So if you were here, and this was your ear, you know, listening to this sound as it came at you, you would hear the constructive interference right there. And that depends on your distance from the speaker from each one, which we're going to call this one R2 and this one R1. Okay? And it depends on the amount of sound you hear from one and the amount of sound you hear from the other in terms of their wavelength. So for constructive interference, you get constructive interference if the difference in path lengths of these waves, meaning your distance from each source, is equal to some integer multiple times the wavelength of the emitted sound if both the speakers are emitting the same sound. Okay, so in this n corresponds to 0, 1, 2, 3, etc. up to infinity. So as long as you position yourself between the two speakers in this way, that you end up with this relationship where they're equal, or they're separated by one wavelength, or two wavelengths, or three wavelengths, you will hear constructive interference. Okay? If not, you're going to hear something in between, and if you're at the specific spot where you get destructive interference, then that's where you get the path length difference is equal to n plus 1/2 times the wavelength, where again n is 0, 1, 2, 3, etc. Okay? So the minimum place where you would receive destructive interference is if you changed your difference in your path length to be equal to n equals 0, 1/2 times lambda. That would be the minimum. Okay? You can figure out different places too, depending on your value of n, but that 1/2 lambda would be the minimum. Okay? So basically, it's as you are listening, this is your ear, okay? Do you hear the sound from the one wave coming in, and do you hear it the same orientation with the wavelengths impacting your ear? If so, then you're going to have the constructive interference. If instead they're separated by 1/2 a wavelength, then that means that you're actually hearing the spot where they're negating everything. Not negating it, I didn't say that quite right, but where they're destructively interfering with each other so that the compression of the one is equal to the rarefaction of the other as it approaches your ear, which would end up giving you completely destructive interference where you would hear nothing. Okay? It all depends on how they add up as it's reaching your ear. And that is expressed in terms of this path length difference right here, as long as they're both giving off the same wavelength. Okay? So it's all about the superposition principle, adding up what you're perceiving, which is somewhat similar to the Doppler effect thing that I was mentioning before, that you can only receive the signal, and your brain interprets what it receives. It can't go back through and make, complex calculations in your head to say, oh, I actually heard this part from this speaker, and I heard this part from this speaker, and so I know exactly what I'm supposed to be getting in terms of both. No, you just hear the net. You hear the result of that as it approaches you. And so now we have to interpret what that means.